Hey everyone, welcome back to the channel. Have you ever wondered how businesses or organizations make decisions to minimize their costs, like production costs? Well, that's exactly what minimization problems in linear programming are all about. In this video, we will walk through a step-by-step example using the graphical method to solve a real-world scenario. You learn how to set up the problem, graph the constraints, find the feasible region, and discover the single best solution that minimizes the overall cost. By the end of this tutorial, you will have the skills to tackle these problems on your own. So let's get started. A cold drinks company has two bottling plants located at two different places. Each plant produces three different drinks, A, B, and C. The capacities of two plants in number of bottles per day are as follows. So we have plant 1 and plant 2. Plant 1 gives you 3,000 bottles of drink A in a single day. It gives you 1,000 of drink B and 2,000 of drink C. Then plant 2 gives you 1,000 bottles of drink A, it gives you 1,000 of drink B, and 6,000 of drink C. A market survey indicates that during any particular month, there will be a demand of 24,000 bottles of A, 16,000 bottles of B, and 48,000 bottles of C. The operating costs per day for running plants 1 and 2 are respectively 600 units, monetary units, and 400 monetary units. That's for plant 1 and plant 2. How many days should the company run plant during the month so that the production cost is minimized while still meeting the market demand? So when you look at this problem, here we have to minimize the total production cost while meeting the market demand. We need to determine the number of days each plant should operate. So this problem can be solved using the graphical method of solving linear programming problems. What do we have to do first? We have to express this problem in a standard form. We have to express this problem in a standard form. So what we are going to do first, we are going to define the variables. So let's start by defining the variables. How many days should the company run each plant? We have two plants, plant 1 and plant 2. So we can let X equal the number of days plant 1 operates. So X equal to number of days plant 1 operates. Then Y equals the number of days plant 2 operates. So those are the variables. So we have to find out the number of days plant 1 operates and then the number of days plant 2 operates in order to minimize the production cost while still meeting market demand. After coming up with our variables defined, then we have to set up the objective function. We have to set up the objective function. So setting up the objective function, the objective we know that is to minimize the total operating costs. Minimize the total operating cost. Already we know that the cost for plant 1 is 600 monetary units and the cost for plant 2 is 400 monetary units per day. So the total cost which you want to minimize is given by the function C equaling to 600, that is 600 monetary units for plant 1, so that is 600x plus 400 monetary units, that is plant 2. So that's your objective function. That's your objective function. So you've defined the variables, you've defined the objective function. Now what next? We have to establish the constraints. We have to establish the constraints. We have to establish the constraints. So we need to go through the question and then we see the constraints that we have. We formulate equations for them. Then after we see what next. So the next step is to we have to establish constraints. Establish constraints. Establish constraints. Now, according to the information we have, you'll see that the production from both plants must meet the market demand for each drink type, that is A, B, and C. So we have the constraint for drink A, we have the constraint for drink B, and then the constraint for drink C. So establish constraints. We have constraints for drink A. Now, when we look at constraint for drink A, we know very well that plant 1 produces 3,000 bottles of drink A per day. Then plant 2 produces 1,000 bottles of drink A per day. But remember, market survey indicates that during any particular month, there will be a demand of 24,000 bottles of A. So our constraint for A is represented by the equation 3,000x plus 1,000y. This is a minimization problem, so this is greater than or equal to 24,000. Then we have constraint for drink B. Constraint for drink B. Constraint for drink B, according to the available information, plant 1 produces 1,000 bottles of drink B per day. Then plant 2 produces 1,000 as well, that is per day. And the total demand for drink B is 16,000 bottles. So this is represented by 1,000x plus 1,000y greater than or equal to 16,000. Then we have the constraint for drink C. According to the available information, we see that plant 1 produces 2,000 bottles of drink C a day, and then plant 2 produces 6,000 bottles of drink C per day. Total demand for drink C is 48,000 bottles in a month. So drink C, we have 2,000 X plus 60,000 Y greater than or equal to 48,000. So those are the constraints which we have for drink A, drink B, and then drink C. But then you also have the non-negativity constraint for the number of days of plant 1 and plant 2. So we have to formulate that as well. It's one of the key assumptions of linear programming. So we have non-negativity constraints. A negativity constraint. So the number of days cannot be negative. So x should be greater than or equal to 0, and then y greater than or equal to 0. So these are the constraints which we have. So we have expressed this problem in a standardized manner or in a standard form. We have defined the variables. As you can see, we have our objective function. Then we also have established the different constraints. Now what's next? What we have to do next is to find the feasible region. We have to find the feasible region. But how do we find the feasible region? We have to graph the constraints. So graphing the constraints. Remember, we have 3,000 x plus 1,000 y equaling to 24,000. So we have to find out what will be the value of x when y is 0, what will be the value of y when x is 0. So when x equals to 0, then it means that y will equal 24,000 divided by 1,000, and that is 24. So here we have 0.4. Then when x equals to 0, when y equals to 0 rather, when y equals to 0, then x will equal to 24,000 divided by 3,000. That's 8. So here we have 8 and 0. Then the other constraint which we have is that is product A. Then we have product B, which is represented by 1,000 x plus 1,000 y equaling to 16. So when x equals to 0, y will equal to 16, and then when y equals to 0, then x will equal to 16. So here you have 0, 16, then 16, 0. The other constraint which we have, that's for product C. That's for product C, which is represented by 2,000 x plus 6,000 y equaling to 48,000. So when x equals to 0, then y will equal to 48,000 divided by 6,000. That's 48,000 divided by 6,000, that's 8. So here we have 0 and 8. Then when y equals to 0, x equals to what? X equals to 24. So this is 24 and 0. So those are the different values of x and y for each constraint. So you should go to put this on your graph. Then you find out the feasible. You find out the feasible region. Find out the feasible region. And then if you have the feasible region, then you can arrive at the optimal. You can arrive at the optimal solution. So I have the graph here, which I've prepared. This is a graph to show the cost minimization number of days for plant 1 and then plant 2. So I have the number of days of plant 2 that is on the vertical axis, and then I also have the number of days of plant 1. Number of days plant 1 operates, that's on the horizontal axis, and that's represented by x. Then the number of days plant 2 operates, that is represented by y. I have my scale here, 1 centimeter equaling to 2 days. 1 centimeter equal to 2 days of plant 1, that's the horizontal axis. Then 1 centimeter equaling to 1 day plant 2 operates, that's on the vertical axis. So due to the plotting, I have the different lines here that represent equations. I have the 1000 x plus 1000 y equaling to 16,000. I have the 3000 plus 6000, 3000 plus 6000 equaling to 48,000. This is 2000 x plus 6000, y equaling to 48,000. Then I also have the 3000 plus 1000 equaling to 24,000. In fact, to make it clear, this 3000, this 2000 plus 6000, this is product C. This is product C. So that's the constraint. Then the 1000 plus 1000 equaling to 16,000. This line, this is product B constraint. Then this is product A. Now, being that this is a minimization problem, you'll be the unwanted region is the region, is the area below this line. The unwanted region is the area below this line, and then the area above, that is the region we are interested in. Okay, yeah, that's the region we are interested in. The region above the line. The region below is the unwanted. Then the region above is what we are interested in, or and call it the feasible, region. Now, the optimal solution will be one at the corner points of the feasible region, and which is the area where all these inequalities are satisfied. You can find these corner points by solving the pairs of the constraint equations as if they were equalities. So what you have here, the corner points we have, I have this as my point A, and at point A you have 0x and 24y. This is at point A. This is at point A, the corner points of our feasible region. That's the region above. Then I have point B, where we have 4x and then 12y. That's point B. Then this is point C. This is point C, this point where you have 12x and 4y. Then you also have D, I can name this D, where we have 24x and 0y. So those are the corner points of the feasible region. So what we have to do, we have to evaluate the cost function, which is, what was our cost function? The cost function was represented by 600 x plus 400y. We have to evaluate the cost function at these points to find the minimum cost. So what we can do next, after coming up with your graph, then we have to evaluate the cost function at these points to find the minimum cost. So calculating the minimum cost, let me do that from here. Calculating, after coming up with your graph, then we have to calculate the minimum cost. Remember, your cost function is represented by C equaling to 400. Is it 400? 600. 600x plus 400y. So you have point A, B, C, and E. Then you have the monetary units. So at point A, let's what we have at point A. At point A we have 0.24. Point A we have 0. This is 0.4. So meaning that your C will equal to 600 into 0 plus 400 to 24. This gives you 9600. Then at point B, what do we have at point B? Point B, you have 412. Point B, you have 412. So your C is 600 times 4, then 400 times 12. That gives us 7,200. Then at point C, what do we have? My point C, I have 12, 14, 12 and 4. X is 12, then Y is 4. So the cost will equal to 600 into 12 plus 400 times 4. And this gives us 600 times 12 plus 400. 400 times 4, that's 1600 plus this is 7200. This is 8800. Then at point D we have 24x and then 0 y. So C is 600 into 24, then plus 400 into 0, and this gives us 600 times 24. This gives us 14,400. So these are the costs at the different points, point A, point B, and then point B. So which of these points minimizes the costs? Of course, when you look at what we have here, is this point B, where we have the minimum cost of 7,200. So we can say and conclude and say the minimum cost is 7,200 monetary units. So this minimum cost occurs It occurs at the corner point B. It occurs at the corner point B, where you have 4 and 12. So therefore, to meet the demand while minimizing our production cost, the company should run plant 1 for 4 days. Company should run plant 1 for 4 days and plant 2 for 12 days. And plant 2 for 4 days, for 12 days to meet demand while minimizing production costs. While minimizing production costs. So that's what the company should do. So they should run plant 1 for 4 days and then plant 2 for 12 days. So there you have it. There you have it. We have successfully solved our minimization problem. We started by defining our variables and setting up the objective function, as you can see, and then the constraints. Then we graphed each constraint to find our feasible one, to find our feasible region. We have graphed each constraint to find our feasible region, and that's the area that satisfies all of the conditions which we have. Then finally, we have tested the different vertices, the region, to find the optimal solution which gives us the minimum cost. Yeah, so this method is a powerful tool for making smart, cost-effective decisions in various fields. So if you found this video helpful, give it a thumbs up. Give it a thumbs up, and don't forget to subscribe for more tutorials like this one. Thank you for watching, and I will see you in the next video. Bye bye.